And yes, I'm very happy to have Glyn Williams-Jones with us today. So Glyn is a professor and chair of the Department of Earth Sciences at Simon Fraser University and co-director of the Centre of Natural Hazards Research. So the Centre of Natural Hazards Research has a broad mandate to conduct innovative training and research on geophysical processes that are a threat to the population and economic infrastructure of Canada. So with all his knowledge, it is going to be amazing learning about Canadian volcanoes. So this is going to be heaps of fun. I hope you all enjoy it. But yeah, thank you so much for joining us today, Glyn. It's really awesome having you here.
Oh, it's my pleasure. And I'm coming to you from Burnaby, just suburbs, well, Port Moody, suburbs of Vancouver. So I'm on the traditional territories of the Coast Salish peoples.
Yeah, I was really curious before we get stuck into the session, what got you into geology in the first place?
Well, surprisingly enough, my father is a professor of geology. So until college, that was absolutely the last thing I wanted to do. But when I was in Montreal, I did a college, their CEGEP program, and my father had said, you have to take this intro geology course with a fellow by the name of Kirk McGeechy. He was a Glaswegian sedimentologist who had his own rock band, a Celtic rock band called Aurealis, and it was phenomenal. It opened my eyes to what had been around me my whole life, and I recognized that being dragged on those miserable field trips really was there. So I then went to rather than going to McGill where my father is still active. I said nope, that's too close to home. So I went to University of Montreal and did an undergrad there. Ended up meeting my now my wife, so it was a perfect decision. And then I slowly went from sort of playing at mineral exploration as an undergrad, and then dove into basically physical volcanology over the years. Bit of a whirlwind tour. Ended up doing a stint in Hawaii for a year and a half. Those worst places to work.
That's
But
amazing.
yeah.
Where have been some of your other favorite places that you've been able to work?
Well, I mean, my pet volcano, if you like, is a volcano. I would argue the easiest volcano in the world to work on. It's called Masaya volcano in Nicaragua. It's about a half-hour drive from Managua, and literally you drive to the top of the volcano and you poke your nose into this crater that has a 400-meter diameter lava lake bubbling away on the bottom, degassing. But it was a beautiful laboratory where we could do all sorts of experiments as opposed to some other volcanoes that I've worked on, like Cotopaxi in Ecuador, summits at 6,000 meters, a lot more effort. So Latin America is where I've done much of my work, Central South America, and now I've got projects here in Canada, but I like to sort of mix it up. So have a graduate student who's from the Philippines. We're working on a Taal volcano there. So yeah, wherever there's something going on, different
You're keen to
angles
go.
keeps me
Yeah.
interested.
I love that. That is so good. So I did ask if you could bring along some pet rocks today, and I think you've got some pretty special ones there to show us.
Yeah. So I'll start with the unconsolidated type. And this is the bag of olivine sand, beach sand from South Point in Hawaii. And so it's a cinder cone that is being basically eaten away, and you've got all of the basalts in the area that have been eroded. And so literally the sand is just pure olivine grains. So and I'm dripping it all over the desk. But so that's the unconsolidated part.
Yeah.
And this one actually was I good luck that I had it at home. This is a reconsolidated, formerly volcaniclastic rock, and it's actually the focus of part of the talk today. So what you can see is these very glassy fragments here, and the ash in between. So this is a welded block in ash flow. So pyroclastic flow that came down from Mount Meager, which I'll be speaking about. And this, in most cases, block and ash flows are too small in volume, and they basically just are distributed and remain unconsolidated. Here, location was important, and this welded itself back together again into this coherent block. And you can actually see some of the cooling joints, sort of relatively coarse cooling joints, that showed that this fragmental material, which welded back in place, also had time to form these kind of small kilometer basalt cooling joints. So it's a really neat fragment. The cat likes to scratch it with his paws, so it's a good way to dampen
Good cat
the
scratcher.
claws. Yeah.
I love that. That is so awesome. Well, thank you so much for sharing those with us. If you want to, get your prezzo up, and
Okay.
I'm so excited to hear from you today. So thank you so much again for joining.
Great. Well, thanks for the invite. I mean, I think this is wonderful. All right. Well, again, thanks for the invite. I really appreciate the opportunity to do this. And really, what I would like to do is sort of take you on a voyage. First, I'm going to wave the flag a bit, specifically to do a shout out that we actually have volcanoes in Canada. But specifically, I want to take you to two volcanoes, Mount Meager and Tse Aks, two very different volcanic systems, and tell you about how we'd be able to bring sort of modern volcanology and collaborate with the local First Nations on whose territories these volcanoes are located, the Lillooet and the Nisga'a nations, and how Mount Meager, or Qẃelqŵelústen in the Lillooet language, and Tse Aks in the Nisga'a language, how we've been able to learn more about these young volcanoes. And again, I would be remiss if I didn't take the second to just really say that this is me standing up in front of you or sitting down in front of you, but it's really the lion's share of the work is by an incredible team of graduate students and collaborators from numerous universities here in Western Canada. So just to sort of set the context, Western Canada, we're on the Pacific Rim, so obviously the Ring of Fire. And the two settings that we'll be looking at, one is Mount Meager. So this is within what's called the Garibaldi volcanic belt. We'll get into that in a second, but very much a subduction zone system. And then the other one further north, Tse Aks, in the Northern Cordilleran volcanic province, is really more of a rifting setting. So broad scale, we've got lots of volcanoes in Canada. Their level of activity is much less than many other countries, for example, what we're seeing in Iceland right now. But certainly we've got all of these volcanoes pictured here erupted within the last 2 million years or so. The issues are access. These are very remote and difficult to get to. But we'll focus on two of the youngest eruptions in Canada, the eruption at Tse Aks, which is really a lava flow system, and then Mount Meager, Qўelqŵelústen, which is much more of an explosive type setting. So to start off, we'll look at Mount Meager, and as I mentioned, the Garibaldi volcanic belt is very much in this subduction setting. We've got subduction of components of the Juan de Fuca and the Explorer plate, obviously fragments of the eastern part of the Pacific plate being subducted under North America. Now, importantly, the Garibaldi volcanic belt is actually the Canadian segment of the Cascadia subduction zone. So we've got a range of volcanic types, but that subduction zone runs about 1,200 kilometers from north of Vancouver, Silver Throne here, down to Mount Lawson in Northern California. The volcano that we're going to talk about, Mount Meager, is about 150 kilometers north of Vancouver, so a couple hours drive. Nice to have an active volcano in my backyard. And the nearest village of note is Pemberton. There's about 60 kilometers east of the volcano. Population is about 5,000 to 6,000 people. Now, one of the key things about this system is the Canadian volcanoes, the vast majority of them have undergone some level of glacial activity. So this really does play a role in a lot of what we see morphologically and geologically. So Mount Meager itself is a large massif. It's long-lived volcanic activity forming over about a 2 million year period. and the volcanic centers have dating is poor because of access issues, but they seem to broadly young as we go northwards. And so the two best and most recent dates, one is this recent eruption about 2,400 years ago, coming off outside the flank of Plinth Peak, and an older one about 24,000 years ago. There's almost certainly been activity in between that, but preservation is definitely a challenge in this glaciated volcanic massif. The other thing that Meager is known for is its extensive hydrothermal system, lots of nice hot springs, and active geothermal exploration. In fact, on the southeast side, sorry, are you seeing my mouse? Okay, perfect. So just on the southeast side here, south of Devastation Peak, there's been active exploration, and some of these wells sort of reach 220, 230 degrees Celsius. So, what would be a very sort of positive numbers in terms of temperature, but also permeability and porosity. But there's other issues here. Now, before I move on, just to keep in mind, we'll be talking about the Upper Lillooet River, specifically around Keyhole Falls. I want you to keep that in mind. And we'll also be talking about Meager Creek. So the massif is sort of bracketed by these two rivers and creeks. So again, this massif is interesting. Given the fact that we've had the subduction of relatively young oceanic plates, the geotherm in the area is quite high, and so we've got quite anomalously high for the Cascadia subduction zone, anomalously high uplift. The result is that we've got this large volcanic massif perched on top of basement. So we can drive along the Upper Lillooet River and see the basement, and then the volcanic edifice perched on top of that. The geology is quite varied, running from basaltic through to rhyodacite, highly eroded, highly unstable. And even though we've been updating the mapping over the last number of years, this is work from a former graduate student at University of British Columbia, it's still spotty. We're either dealing with glaciers, so a lot of undivided volcanics here. We just haven't had the access to be able to get into the detailed stratigraphy and volcanology. But we're getting there. We're chiseling away at this over many decades now. Now, it is the site of Canada's most recent large explosive eruption. And what I want you to keep in mind is the 1980 eruption of Mount St. Helens. It was very much on par with that. So between 0.8 cubic kilometers in comparison to about 1 cubic kilometer of erupted material. So picture in your mind an initial eruptive phase. We're jetting an ash column 15, maybe 20 kilometers into the air, and pyroclastic density currents or pyroclastic flows are coming down the flanks. The eruption column is collapsing in components, and we're getting widespread airfall of tephra and large deposits of pumice. The airfall was significant to the point that there's areas in proximity to the volcano that reach 60 to 80 meters thick of tephra and pumice, to the point that there's actually 2 small active quarries for pumice. The finer material, again, pumiceous tephra, was sent about 530 kilometers east into Alberta, so actually probably reached the main cities of Calgary. And we can see some other examples for some larger events, say the Mount Mazama eruption about 7,000 plus years ago, Crater Lake. So, a fairly large, significant eruption. And here's just a visual from the 1980 eruption at St. Helens to give you an idea of what we would have been seeing. The story is interesting because it transitions from an initial explosive phase, in fact, into an effusive phase where we have a viscous plug of rhyodacite pushing out from that initial explosion crater. You can see just a schematic here, And we're oozing out this dome, so transitional lava flow coming down the flank of Plinth Peak, so the northeastern side of Mount Meager. And eventually that hot, probably 800 degrees Celsius material fails catastrophically, and it breaks apart into this welded block and ash flow material. So we're basically fragmenting this dome of lava into chunks the size of cars and then ultrafine ash in between. And rather than spreading out as it would on another volcano, comes down into the Lillooet River Valley, has nowhere to go, and bulks up. So it bulks up to form a dam 110 meters high and 3 kilometers wide, and it welds itself back together again. So the upper Lillooet River is a significant river, and over a period, we believe, of maybe a few months, we now have formation of a temporary reservoir behind this impermeable dammed welded block and ash flow. Over the course of those couple of months, we've also had, and we can just see here in the lower left, an example modern day shot of what's called Keyhole Falls. So we can see this welded material, and you can maybe make out some of the cooling joints that we see on the small sample, and this pile of unconsolidated material volcaniclastics sitting on top of the welded dam. Now, this is the remnant following a catastrophic outburst flood. So modeling by my friend Kelly Russell and one of his former postdocs, Graham Andrews, suggests that as this dam built up, saturated the unconsolidated material, eventually we get a nick point, a slurry has developed, and a nick point forms in this welded material, and we start getting rapid incision and a catastrophic unzipping and failure. And so modeling by Graham suggests that the 2.5 kilometers of this welded material unzipped in potentially as short as 8 hours, which is absolutely mind-boggling. But we can see car-sized deposits of this, what would have been still hot welded material 35 kilometers downstream, and cooling joints, radial cooling joints all the way around. So it was still hot when it was in place. And what we can see here, Keyhole Falls, this little slot is what has been eroded in the last 2,400 years since the formation of that dam. And that is, for scales, about 3 or 4 meters wide. Amazingly, some idiot actually kayaked off that down the waterfall. Absolutely, and they say volcanologists are crazy. So history has a tendency to repeat itself. Along with being Canada's most recent large explosive eruption, it's also the site of Canada's largest ever landslide. So in 2010, we had failure, non-volcanic failure, of about 53 million cubic meters of rock into a rock avalanche, transitioned into a debris flow, temporarily dammed the Lillooet River yet again, and eventually that failed over about a day and a half, but led to widespread flooding downstream in an area called Pemberton Meadows, and the temporary evacuation of 1,500 people. Now you're asking, why the hell do I have the pyramid down there in the right-hand corner? Well, I'm sick of using swimming pools as analog. So 53 million cubic meters is about 20 times the volume of the pyramid of Cheops. So the elephant in the room with this very large massif is it's a big, rotten, unstable mass of rock. And work by one of our former graduate students, PhD students, Gioacchino Roberti, using satellite radar mapping and monitoring, identified well over 27 slopes on this central volcanic complex that are moving, where we have motion. And the 2010 here is in yellow. This other one, Plinth Peak, is another one that we're actually quite concerned about. It's this example in the lower right, that orangey area. This is an area that we've seen move on the order of 3 centimeters over a matter of a month or two in the summertime. And depending, if you just sort of trace out the area and take a guesstimate of depth, it could be potentially up to 300 to 500 million cubic meters. So maybe 10 times the size of the 2010 failure, of course, if it was to fail, consistently. So again, just to locate us, lower right here is Meager Creek. We've got the upper Lillooet River coming here, and just so that big red slide would come down Job Creek and into the upper Lillooet River, and basically about 4 kilometers of traveled path, we have a $500 million hydroelectric run-of-river facility. So there's infrastructure that is absolutely at risk. It's not an inactive volcano by any means. Serendipity is a wonderful thing. And in 2016, there was a helicopter pilot flying over the area with a group of biologists. They were doing a mountain goat population survey. Turns out the helicopter pilot, Hannibal, great name, was a geologist. He'd done his undergrad at the University of Victoria here in British Columbia, saw these glacial-volcanic caves, fumaroles, with volcanic degassing. So we got into a helicopter and had a look-see, got the seismologists to go back into the catalog and see if they could find something. Unfortunately, the monitoring for Canadian volcanoes is pretty much non-existent. And so the seismic network is really for tectonic events and not optimized for volcano monitoring. So maybe there was a little swarm of activity in 2014, but it's a bit wishful thinking, unfortunately. So again, we got excited. Got a volcano that I can go do something on just up the road. So we started doing volcanic degassing surveys, as well as a suite of other geophysical and geological mapping. And most recently, we, with luck, were able to coordinate with a team of expert cave search and rescue people, as well as a team from NASA, who want to use this as an analog for testing their robots. But they went into the ice caves. These are 40 to 50 meters deep, changing every year, especially with some of the melt that we've been dealing with. But Christian and Katie were able to go down in toxic levels of hydrogen sulfide and carbon dioxide. Thus, stupid volcanologist, I stay on the outside and let the experts go in and do the dirty work. But they found the source. They saw tiny, beautiful little crystals of native sulfur, low temperature fumaroles, about 90 degrees Celsius, so around boiling for this elevation. But importantly, 100 ppm, over 100 ppm of sulfur dioxide, which suggests that there is a shallow-ish 3 to 4 kilometer deep magma system that is still active or present. It's not a very much inactive system where we would just expect to see, say, hydrogen sulfide coming out. So lots of work to do there still. And another thing that we're trying to do, knowing that we've got this active volcano in our backyard. So again, in blue now is the Meager Massif, and just northwest of it is a little basaltic flare-up that was Holocene. We don't have good dates on that. But this is the work of one of my current PhD students, and looking at some of these little olivine crystals, but in this case, collected from glassy, subglacial or glacial contact lava pillow rinds. She was able to tease out these little olivine crystals and then make measurements of the rate of diffusion of iron and magnesium across the boundaries and use this as a clock to give us a time of residence. And so she's been building up an archive of crystals that has now been able to pin down the fact that there was a residence of about 1 to 3 months in the shallow magma system. We think about 3 kilometers just before it erupted. So for the first time in Canada, we have at least the start of a clock that can tell us if we were to have renewed activity, this is the kind of time frame we might be working with. So another push for some volcano monitoring. So at that transition, the fact is our monitoring is poor. Thanks to really a public-private partnership between local corporations who donated instrumentation, time, money. Installing that telephone post is about $30,000 worth of post and manpower and helicopter time. We've starting to just inch towards having some nascent monitoring. So in the lower right, we have an image from one of our cameras overlooking the fumarole field. We're starting to test seismoacoustic sensors, little actually citizen science scale sensors, to try to capture some of these debris flows, and integrating satellite monitoring, trying to develop a multifaceted approach to things. Natural Resources Canada are starting to help there, especially on the satellite side of things, but we've got a long way to go to compare to many sort of countries with active other active volcanoes. And again, one of my push is to get all of this information accessible and in an open access format. So still working on a very beta natural hazards data portal that is open to the public, where you can actually go and see those images, as well as weather data and all sorts of other real-time data sets. So one of the key things that with all of the work that we've done on Mount Meager to date is there's also this wealth of local knowledge that's been preserved over many, many generations of this long-lived volcanic system. And in the Lil'wat Qẃelqŵelústen, which is their oral traditions, their oral histories, they preserved, say, one story here called the Copper Canoe. It's well known in the area, speaking about two shaman brothers living nearby, having a dream of canoe travel and traveling down the Lil'wat River, but being stopped by a dam, that welded block and ash flow, then being forced to make a hole and a slot canyon to allow their canoe to pass, heading down the Lil'wat into the Fraser River and out to the ocean to then bring back salmon that had been blocked by this eruption. And again, these observations have been also aligned with other biological and studies and so on. There's many, many other stories of direct observations of the eruption, of fumarolic activity, and even earlier landslide events. So it's a wealth of information that we're only just starting to grasp and see the true benefits for both the local communities and the scientific communities. So we'll jump further north to another volcano, Sii Aks, geologically, tectonically very different. We're now into a rifting center. So we've got this large transform fault, the Queen Charlotte transform fault, and inshore, the Northern Cordilleran Volcanic Province is very much an extensional environment. It's statistically the area with the most frequent volcanic events, about averaging an eruption about every 250 to 300 years, and the second most recent eruption in Canada, that of Sii Aks, about 1700, so call it about 300, 350 years ago. To the best of our knowledge, it's potentially also the most dangerous and deadliest volcano, with possibly up to 2,000 fatalities in 3 villages of the Nisga'a Nation. Those numbers are sort of difficult to pin down with any detail. Now, Sii Aks is a really innocuous little volcano. The actual cone itself is only about 80 meters high, but what's impressive is this incredibly long lava flow, 32 kilometers long, channelized, worked by my former graduate student, Yannick Lemoine, estimated the volume at about half a cubic kilometer. And what was really special is, again, location. Just like that block and ash flow from Meager, here the lava flow flowed so far because it was immediately channelized into just south of Sii Aks, or southwest, into Crater Creek, then entered the Sii Aks River Valley before flaring out into the much flatter Nass River Valley. And one of the towns is Qვითelquen and Nuayanch as sort of examples here. So if we look from Qვითelquen, from that plain, so the north looking south, in the lower, we can see this incredible pavement of ultra flat lava plain, and the Nass River that is just literally looks like it's being cut by a knife. So I want you to keep that in mind. Now, what was really special about this area is, given its youth, there are really, really well-preserved oral traditions. The Nisga'a Arawak, that have detail that we were able to use to help inform our modeling and better constrain what we think were the sequence of events. So the Niska Arawak, and again, this is information that the Niska Nation has shared publicly on their webpage, and the local communities have given us permission to share this. We don't ever share information that is their stories, their private stories to share. But broadly, what we have this story about Lakshmil, which is where the fire ran out, and children were seen being disrespectful to salmon. Salmon are a major food supply and extremely culturally important. And they were placing flaming sticks and pieces of flint in the fish and letting them go by. An elder came along and warned the children to not do that the salmon would curse them, and that the creator would be angered. Unfortunately, as is often the case with children and teenagers, they didn't listen. And very soon after, there was a ground shaking, and a local, essentially lava or fire spirit was released and sent the lava flows down the river valley. Locals in the area, in panic, fled up to the mountains. Some tried to canoe across the river, but perished. The Nass River is the third strongest river in British Columbia. It's really a sight to be seen. Now, as the event was ongoing, preserved in the Arawak, a local spirit, a protective spirit of the villages, was awakened and came to do battle with the lava god or the lava spirit. And Qўelqŵelústen suddenly emerged, started to use his long nose and blow onto the lava, and over a period of days, there was smoke to be seen blowing, and eventually the lava flow cooled into its present state. Now, thanks to the work by Yannick, piecing together information from the stories and from other writings of subsequent missionaries, we have a good idea of the paleo setting of the Nass River in this area. So Crater Peak is the one that I want you to think about. The Sii Aks River Valley, there was one fish camp where local members of the community would prepare fish, another smokehouse, again for preserving, and then 3 villages. The exact location of those villages is unclear, but this was what was understood to be the pre-eruptive location of the river valley. And then numerous work originally in the 70s and then massively expanded upon by Yannick, led to this detailed mapping of 4 lava flows that make up this 32-kilometer flow field. So a question that we went in, knowing about the oral traditions, there had been some scientific publications that suggested there might in fact be multiple eruptions. And of course, that could have hazard implications. So we went in there. Was it 1 event, 2 events? What could we say about the style and duration of the eruption? Could we say something meaningful about the eruptive volumes, and maybe something about the plumbing system? So Yannick and collaborators from UBC, Douglas College, and in the UK as well, led to mapping also of this very innocuous little cinder cone here. And we can actually see the lava flow here in the lower left, a few little satellite cones that had developed, and a spatter rampart that again I'll speak to in a moment. So this is very much at the headwaters of the lava flow and the onset of the eruption. So how do we do this? Well, thankfully we've got somebody like Yannick, who's a meticulous field mapper and an artist. So having the two in one was just a godsend for me. I'm a terrible artist. You'd see squares if it was me, sort of crayon cartoonish type stuff. So Yannick's work was absolutely meticulous, and access was good. This is a young eruption, so we were able to go in and with numerous field assistants, go and add to our understanding of the emplacement of this lava flow. And it ranges from what we call hummocky pahoehoe, pahoehoe being the classic Hawaiian term for lava flows, often ropey, lava flows, but also here seeing very planar, flat pavement-like material, some pressure ridges that had built up and compressed the already brittle material, leading to these slabs, many lava tubes that had also then collapsed. And Yannick is now actually working on an automated classification system for this using surface roughness down to the millimeter scale. So he's working on using this and what we've learned from Sii Aks, this detailed mapping, to actually apply to other volcanoes, other lava flow fields globally, and maybe even extraterrestrially. So the detailed map, you can't really see it at this scale, but it's incredible, absolutely super detailed, and that's a resource that we could build on to better understand the source. Now, of course, given that detailed mapping, we were also able to do detailed geochemistry. And what Yannick was able to do to try to address that question of was there one eruption or two eruptions over, say, a multi-hundred-year time period, he grabbed samples from all four flows, the whole length of the flow, and from the eruptive center at the source. And it's the most geochemically boring, consistent suite you can see. So it comes out as a basanite, iron-rich basanite trachy basalt. But when you look at the rare earth element, this spider diagram, what is amazing is how incredibly consistent those analyses were for these four different flows. So this gives us the confidence that there was absolutely, there had to be only one single batch of magma that erupted over a very short period of time. There was no long storage time and time for, say, fractionation to get going there. So doing a lot of geochemistry and petrology, he was able to bring up a story of the sourcing, this rifting environment, getting these sort of basanite material, working its way up, probably eventually at the Moho, going through small amounts of partial melting, only a few %, and then eventually reaching probably a 5 to 6 kilometer storage area where there was a crystal fractionation. And so lava flow 1 and 2 are very, very crystal poor, and lava flow 3 and 4 are very crystal rich, seeing these large plagioclase on the order of 2 to 3 centimeter long crystals, but all happening in a very, very short period of time. So we've got a handle on, and this is just skating over the surface of the detailed work that he did, but quite hot, about 1100 degrees C, 1080, 1090. And now we're starting to be able to say something about the viscosity of the flow. So here's a numerical model that Yannick put together. Now the key factor is we took the paleotopography, and then the starting point was the flux of the river, of the Nass River, 700 cubic meters per second, based on sort of modern values, would be very similar just a few hundred years ago, and estimates of the viscosity, the temperature, density, and reasonable flux from the vent at Sii Aks on the order of 1,500 cubic meters per second. Now, it sounds like a lot, but to put that into context, right now in Iceland, in a similar rifting environment, there are measured effusion rates pushing 7,500 cubic meters per second. So this is absolutely well within the, plausible. So by running this model with only those initial starting parameters, what's amazing is the model replicates the push, the movement of the Nass River northwestward to its current setting, and essentially replicates about 80% of the flow emplacement. So the model does an extraordinarily good job of replicating what we see. So it gives us confidence in the numbers. And using those numbers, we're able to start to look at how fast this flow was coming down the channel. So it's channelized, it's coming relatively fast, but in most cases, you could outwalk this. However, if you're people living in the area who've never seen this kind of event, it would absolutely be shocking. And so initially high effusion, but relatively low velocity, reaching, say, the first fish preparation area in as little as 4 hours. That's not a lot of time, especially if you don't know what's coming at you. About, after about 10 hours, we're getting into the Nass River Valley, and then things really slow down as the angle drops, and we get this interaction with the river. But clearly, these villages being significantly impacted, and so in a matter of just a few days, certainly not months to years, we have the emplacement of the entire flow package. So that is really incredible and understandable why we could have potentially such high number of fatalities. So again, trying to tease out the different aspects of the story in the Arawak, the preserved oral traditions, there was mention of villagers seeing glows and clouds of smoke up in the sky. Now, if you're in the Nass River, to be able to see that, what Yannick was able to test using what's called a viewshed analysis, he just took the current topography and what would a person standing by the river see if they were looking towards the volcano. And to be able to see that eruptive column, what we suppose is eruptive column, it would have to be at least 5 kilometers high. So we've now got some constraints that we can put on the eruptive sequence of events. And this matches actually quite well with some other independent theoretical models based on other similar types of eruptions. So again, it's wonderful having an artist for a graduate student. Here's our starting point, our paleo setting, the untapped eruption, and we start the initial phase. This effusion of about, say, 1,700 cubic meters per second, a wall of lava fountaining up, maybe up to about, say, 100 meters, maybe 120 meters, along a fissure about 750 meters long. And all of that material raining down, this high flux of material raining down, forming a lava flow, immediately being channeled and probably reaching the Nass River, and it's the maximum flow in about 3 days. So really a spectacular event. Subsequently, again, because of the detailed mapping, we know that there was a second flow, original name, flow 2, much lower flux, again, unsurprising as the gas volume is starting to wane, but it's overlaying the original flow, flow 1, flowing down the valley and reaching its extent in a period of about, say, 4 days. At the same time, we are starting to get coalescence of the fissure into smaller chunks, what eventually formed 2 small satellite vents here, and then this very large spatter rampart that wraps around the main cone, and of course buoyant sort of degassing scoria ash plumes rising up into the air, probably again maybe 100 meters or so. The final episode is sort of the placement of two flows, flow 3 and flow 4. These are these crystal rich ones, these large lats of plagioclase floating in them, and we can see that they really don't make it very far. Again, not surprising. The viscosity is higher, there's less gas in the system, and they just trundle down the valley. The one flow 3 barely makes it out of Crater Creek, the other one doesn't. And one thing I didn't mention in here, there are these incredible lava balls that are ranging between 50 centimeters and 5 meters in diameter. And just think of a snowball rolling down the lava flow. And there's about 300 to 500 of these things. We've never seen them anywhere else in this quantity in the world. So this innocuous little Canadian volcano is oh so special. So bringing this all back, why am I so excited about this? Well, they represent two of Canada's most recent volcanic eruptions. Sii Aks only about 330 years ago, Qўelqŭelústen, Mount Meager 2,400 years ago, but again, on the scale of the 1980 eruption of St. Helens. But really what is so powerful is the alignment of the records of observational information preserved in the oral traditions and how this provides foundation for the scientific assessment, the volcanological assessment, constraints on those numerical models based on the oral traditions. And then finally, it's a plug. We've got We actually have lots of volcanoes in Canada. They're active. They're still really poorly studied. So if you've got full graduate students that are excited, send them my way. There's lots to do. And so with that, I'll say thank you and open it up to questions.
That was awesome. Thank you so, so much.